So as of mathematics, now we're with paragraph 2, a rough classification of Lie algebras. So this corresponds to chapter 4 of the book. Chapter 1 and 2, I talked about them last Tuesday. Chapter 3 answers your question about what are all the Lie algebras of dimension 3, but I'll skip this. So it's if you are interested, you can read chapter 3 and read about the 3-dimensional and 2-dimensional Lie algebras. So let's get an overview over the Lie algebras, and we start with the definition. So fix a Lie algebra L. And given this, we define the derived algebra. This is denoted by L prime as follows. Take the set of all commutators x, y, where x and y are elements of the Lie algebra, and then we take the vector space generated by the set. So this is a vector subspace of L. Maybe all right, this is definition and lemma also. So the lemma part is that this is an ideal. And again, definition part, the derived algebra. So maybe I comment later on the significance of this, but let's just start with a proof. So this way we can derive also what an ideal is. So first thing is it should be a subspace. Well, this is obvious because it's the subspace generated by some set. So what's really the point here to show is whenever I fix some element x in this derived algebra, x should be in the derived algebra, and y an arbitrary element of the total Lie algebra, then the commutator should still be an element of the derived algebra. So this is the definition of being an ideal. And note again, in particular, if I've proven this identity for all x in L prime and y in L, in particular I've proven it for x in L prime and y in L prime also. So this is a subalgebra, and this is why it's called the derived algebra. So in particular, L prime is then a subalgebra of L. Yeah, how do we do this? Yeah, this is just true. This is even a generator. So we have to show that any such element is contained in L prime for x in L prime and y in L. Well, but if x is in L prime, then it's for sure in L. So so it's even a generator. So this is not really difficult here. Good. Um, so why do we want to have this property? This is an ideal. This is one of the new exercises. So if I is an ideal, then I can consider the quotient vector space of coset classes, an element plus the subspace. And this becomes a Lie algebra. By, of course, now I have to define the bracket. So say I take some coset classes x bar and y bar. So this is maybe, if you prefer the other notation, this you can write them as x plus y respectively y plus I. So you want to define the bracket, and you just take representatives x and y, calculate the bracket of those. So this is the bracket in L, and take the coset class of the whole thing. And of course the crucial thing to show here is that this is well defined. So it doesn't depend on the chosen representative. So I put this on the second exercise sheet, exercise 2. So this particular ideal is connected with abelian Lie algebras as follows. We fix any ideal in L, and then the statement is the following. I can always consider the quotient Lie algebra as defined here. And I can ask myself, when is this abelian? Well, and the property is this is equivalent that the ideal contains the derived Lie algebra. All right, let's prove it. And again, maybe I'll recall. Abelian for Lie algebra means that the bracket of any two elements is 0. So let's start with a direction from right to left. So we suppose that the ideal we quotient out contains the derived Lie subalgebra. And we fix two elements of L, and of course we want to compute ultimately this commutator in the quotient algebra. What do we know? Well, the commutator is, of course, by definition, of the derived algebra, an element of the derived algebra, even a generator. So it's also an element of the ideal I. Yeah. And that means, in other words, the class of the commutator is 0. And the class, this was just the definition of the bracket on the quotient. This is exactly, sorry, the commutator of x bar and y bar. So this is it. Yeah, the converse is not much more difficult. This is so now we suppose that L mod I is abelian. That means x, y equals 0. For all classes x, y, so for all representatives. And again, by definition of the quotient algebra, this just means that the commutator x and y is contained in I for all x, y, and L. Yeah. So I is an ideal. In particular, I is a vector subspace. L prime is the vector subspace generated by these elements here. So it's the smallest vector space which contains all these elements. So in particular, it must be contained in I, because I is a vector space which contains all these elements. Okay, so this was more or less a warm-up. And now what one wants to do is to iterate this construction. So one starts with a Lie algebra L. And from this, one defines the following sequence of Lie algebras. L upper 0 in parentheses is just L itself. Then L1 is the derived algebra. L2 is, well, you take L1 and 4. This is a Lie subalgebra of L, so it's a Lie algebra, so we can do the same construction and take its derived algebra. This is L2, and so on. Then L3 is L2 derived. So we form an infinite sequence of Lie algebras, each one contained in the previous one, and this is called the derived series. I don't understand why it's called series. It's a sequence. There is no sum, but anyway, that's what it's called. And now the so, well, maybe I said it's an infinite sequence, but of course all these are vector spaces. So, well, suppose in most cases we are interested in this lecture at least, the Lie algebra L will be a finite dimensional vector space. So in this case, at each step of the iteration, either that dimension goes down or it doesn't. And it can only go down finitely many times. If we started with a with a finite dimensional vector space, so even though this is defined as an infinite sequence, it will become stationary at one point. And there are two possibilities. Either it will become stationary at a non-zero vector space or at a zero vector space. And this is the property for which we introduce an extra name here. Then L is called solvable. If it becomes zero eventually, this series, if there is an M, Lm. Yeah. So if you studied Galois theory, maybe you know this property. So this is the exact analogous for groups being solvable, and there it's connected to equations being solvable, and this is why it's called solvable. Yeah. So from this definition, it's not clear why you choose this word to denote this property, but it's for Galois groups, this is connected to solvability of equations, but well, these continuous groups or Lie groups never occur as Galois groups, as far as I know. So, well, so I think the best thing is just to take it as a definition. So. But in fact, so I didn't want to talk about Lie groups anymore, but let's just give me one reference at least. So if you're interested in the connection with Lie groups, because possibly you heard about solvability of groups, and so in fact there is a theorem which states that solvability of a Lie group is equivalent under certain conditions to solvability of the Lie algebra in this sense. And you can read about this in Procesi, Lie groups, chapter 4. Section 7.1. So anyway, but let's for now just accept the definition and rather look at an example to get a feeling for it. Consider fancy B. The set of strictly upper triangular matrices, say with complex coefficients. So this is a sub-Lie algebra of GL3C. Yeah, so let's compute the commutator. So the derived subalgebra. So I just take any two elements. what's that? Well, let's just use the definition of the matrix multiplication for the first sum, and it's this matrix times this. So to form these products, so you see directly that over here everything will vanish also. If I compute this component here, it's 0 times a, and then here it becomes 0, so this is also still 0, similar here. But for this component, something will appear, namely a c tilde. Minus the product in the other direction. Well, and then, of course, the zeros remain, and it's a tilde c then. So this commutator is a matrix which has zeros everywhere except in its upper right corner. And of course there, if I choose, as I can still choose A, B, C, D, and that tilde versions arbitrarily, so I can obtain an arbitrary scalar here as the difference A, C tilde minus A tilde C. So so the derived algebra is exactly the Lie algebra consisting of these matrices, having an arbitrary component in the upper right corner and 0 everywhere else. So the next step would be to compute the derived algebra of this one. Well, in here, so I don't want to write everything down again. So now it's the same thing, but here are zeros. And yeah, so if you do the computation, you see that you get zeros everywhere here. So the second derived subalgebra is already 0. So in particular, B is solvable. So the other example is a counterexample for a Lie algebra which is not solvable. Let's consider this favorite vector product Lie algebra. And you can easily calculate. I think maybe I also put it on the exercise sheet, or anyway, it's easy that you can have the following relations. Wait, just make sure that this is the example I wanted to do. Yeah. So EI are the standard basis vectors. EI and E2, the commutator will be E3. E2, E3 is E1. And E3, E1 is E2. So you can verify this identity easily. So E1, E2, and E3 are all contained in L prime, and L prime is a vector space. It's the vector space generated by at least these two vectors, which are a basis of R3. So L prime is L in this case. And then, of course, this sequence becomes stationary at L. So every component of this sequence is L. So L is not solvable. Good. So we wanted to have a rough classification, and the solvable Lie algebras are the first class of Lie algebras in this very rough first classification. And now let's try to find the complementary class, so which are the other Lie algebras. And for this, we need the following also definition and lemma. Again, we start with an arbitrary Lie algebra L. And then consider the following set of solvable ideals. So Lie algebra, so it has some ideals, and each of them, as it's an ideal, it's also a Lie subalgebra. So it is, by definition, either solvable or not. And I just consider the set of solvable ideals. And the property here is this has a greatest element. So greatest with respect to inclusion. That means, in other words, there is a solvable ideal which contains all solvable ideals. And this is called, so this was the lemma part, now the definition part. This is the radical of L, and it's denoted just by rad L. Yeah, so this is the first non-trivial proof here. How does it work? So what we have to show is the following. Whenever we have solvable ideals ij, then we can find a third solvable ideal k. Well, such that k contains both of them. I and k contains j. So this is just the statement in other words. So I want to show that there is one greatest. So for any two, I have to find one which contains them. Maybe. Well, let's just try with the most natural one, maybe. Let's consider k I plus j. So this is the set of all x plus y, or x is contained in I, and y is contained in j. So the claim is such, or this set fulfills the property. So there are several things to check. Some of them are indeed obvious. So I have to check that this contains I and j. This it does. For example, it contains I because j is an ideal, so it's a vector subspace, so it contains the 0 elements. So I can put y equal to 0 here, and then I have just x. So, and similarly for j. So this is clear. So then the K is a vector subspace. It's also clear. Why is it an ideal? This is also clear. So let's just do the computation. So I fix an element of k. I can write this as x plus y for x and I, y and j, and take an element z of the Lie algebra. So I have to consider now the bracket z xy, and I have to show that this is still contained in I plus j. So why? Because the bracket is bilinear, so I can write this as zx plus zy. So this is linearity in the second argument. So x was an element of I, and as I was supposed to be an ideal, the whole thing here is still in I, and here similarly. Y isn't j, and as j is an ideal, this bracket isn't j, so the sum is an I plus j. So this was also easy. So now it's the hardest part. K is solvable. How do we do that? So there are several steps here. The first step is, well, we know J is solvable. And I claim from this we can conclude that the quotient J mod I intersected with J is solvable. Yeah. Okay, so in the book everything is a bit more elaborate. So there are some elementary things to check, which I don't do, but we checked enough elementary things today. So this intersection is still an ideal, and it's an ideal in J. It's contained in J. This is also clear. So this quotient makes sense. It's defined as I defined it before. The Lie bracket is well defined in the quotient. And yeah, I want to show that this quotient Lie algebra is solvable. let's just think about how we compute the derived series of this quotient. So let's say we want to compute the mth derived Lie algebra of this quotient Lie algebra. How do we do it? Well, for each iteration, we take the vector space generated by any two elements of the quotient and compute the commutator, and then take the vector space generated by all these elements. So, but in practice to compute, we always compute with the representatives. So actually the computation we do is in J, and then we just write in the end all our computations have to be interpreted modulo I intersected with J. So indeed, to compute this is the same computation as if I just wanted to compute the mth derived Lie algebra of J, just modulo I intersected with J. So what does it mean, just modulo I intersected with J? So that means some additional elements become 0. Namely, all the elements of I intersected with J. So even if I compute the derived series without the quotient, so without having these additional 0 elements, at some point this sequence will be 0. Well, computing in the quotient will make it even easier for elements to become 0, because whenever I come into this ideal, an element already counts as 0. So from this it follows that eventually the mth derived algebra of the quotient will become 0. Yeah, so this is one of the things which is not, so I didn't do this totally formally, and if you're not used to algebra, you might be confused by this. Is anybody confused by this, or no? Good. Now, next step. The claim is the following quotient. Take I plus j, so this is k in other words, and quotient out by I. And the claim is that this is isomorphic to this Lie algebra we considered here, j mod I intersected with j, so both are quotient Lie algebras. So these are isomorphic as Lie algebras. Hence, here the left thing is also solvable. Indeed, maybe you know from linear algebra that these are isomorphic as vector spaces, so I won't prove this now, but I'll write down the map, the isomorphism. So this is easier to define the other way around. So I send a coset class here. So coset class with a representative x is just sent to the coset class with a representative x here. So this is an isomorphism of vector spaces. See linear algebra, or do it as an exercise, or ask me later. And and preserves the Lie bracket. So this is now the new observation. This preserves Lie bracket. So it's an isomorphism of Lie algebras, and yeah, this definition being solvable carries over. Yeah, last step. So far we've shown that this quotient is solvable. And from the beginning we know that the ideal I is solvable, because this was in the assumption. So I claim here that from this I can deduce, in fact, that I plus j, so k, is solvable. And this finishes then the proof, because this is what we had to show. Yeah. So the first property, this quotient is solvable, means there is an M such that I plus j mod I, the mth derived Lie algebra, is 0. So let's interpret this in terms of representatives. If the mth, so it's again another trick. I know that calculations in the quotient algebra are just calculations with representative, and in the end I mod out I. So if I mod out I and obtain 0, that means if I don't mod out I, then I obtain something which is contained in I. This just means that after modding out I, everything vanishes. So remember this construction of this derived series. At each point, I take the derived Lie algebra of the previous component of the sequence. That means I take any two elements of the previous component, form the commutator, and take the vector space generated by this. And this immediately implies that we have some monotonousness property. Yeah? So if I plus j m is contained in I, then it follows that I plus j m plus 1 is contained in I prime. Yeah? Sorry, this is m plus 1. Well, just because this thing is generated by all commutators of elements of I, and this thing is just generated by some commutators of elements of I, namely those which are already contained in I plus jm. Yeah? And so on. So this inclusion carries over I plus j, the m plus second derived Lie algebra is contained in I 2, and so on. Huh? So I was solvable. How do I write it down? So there is an n such that in is 0. This is because I was supposed to be solvable. Hence, I plus j to the m plus n. By this reasoning, this is contained in in, which is 0. So this thing is 0. Good. So now we can define the second class in our rough classification of the algebras. Namely, the Lie algebra L is semi-simple. Two properties here. First, L must not be the zero Lie algebra. It's kind of a trivial example which one wants to exclude here. But the radical of L should be the zero space. So again, the radical was the greatest solvable ideal contained in L. And we just proved that this exists. And it's, let's do an example. Again, this vector product Lie algebra. Claim, so this is R3 with the vector product. Claim that this is semi-simple. Well, it's non-zero. That's good. And so I have to show that the radical is 0. So I have to show that the greatest solvable ideal is 0. So in fact, I have to show that 0 is the only solvable ideal. So the first thing is maybe to get an overview of all the ideals of L. So I put this on the exercise sheet, 2 and the third exercise. Then you can easily see that, in fact, there are only 2 ideals at all. Namely, the zero space and L, the whole space. And in fact, that these are ideals is clear. So this is, for any Lie algebra, the zero space and the whole thing are ideals. So that these are ideals is not astonishing, but these are the only ones. So I don't prove this here, but you can prove it as an exercise. So we just have to check which one of them are solvable. Of course, the zero ideal is solvable because it is zero, so even no derivation is necessary. And as I've shown above, L is not solvable. So see above. So the greatest solvable ideal is the zero ideal. So the radical is 0. So all the conditions are fulfilled, and this is a semi-simple Lie algebra. So the last lemma for today is to show in what sense these 2 notions we introduced complement each other. And in fact, in a sense, they do. So we start, as always, with an arbitrary Lie algebra L. So the radical is the greatest ideal which is solvable. In particular, it's an ideal. So I can form the quotient algebra. And the claim is that this is semi-simple. Yeah. So maybe before proving it, I just give the interpretation. So you should think of this as a Jordan-Holder series. Or something like this. So if you have an arbitrary Lie algebra, this contains the radical. This contains the zero space. So somehow there's this sequence, the filtration, and the quotient here in the upper part is semi-simple. And the quotient here in the lower part is new solvable. So in this sense, any Lie algebra is built from these building blocks. So again, this classification is not in the sense that each Lie algebra is either semi-simple or solvable, but rather each Lie algebra can be decomposed in a semi-simple quotient and a solvable sub-algebra. So, but let's prove this. Well, we want to show that this is semi-simple, the quotient algebra L modulo the radical. This means we have to show that the quotient algebra does not contain any non-trivial solvable ideals. So by J bar, I mean any solvable ideal and of course then we have to show that J bar is 0. So this amounts to proving that every solvable ideal is the 0 ideal. So this Lie algebra is semi-simple. There is this. Didn't think of this property. So I have to suppose that L itself is not solvable. Right? Because if L was solvable, then the radical would be the whole thing, so the quotient would be 0, and then by this part of the definition, the quotient would not be semi-simple. Okay. So we suppose L is not solvable, and then all we have to show is that the quotient is 0. So I define the following set J. All elements of the original Lie algebra L such that the class of X, coset class of X, is contained in this solvable ideal of the quotient. So this is a subset of L. So it's always the same trick here, playing with these computations in the quotient and computations with representatives. So we know J bar is solvable. That means there is an M such that J bar to the M equals 0. Well, what does it mean? For this M, if we just compute J to the M, this should be 0 after modding out the radical. So J to the M must be contained in the radical. So now it's the same trick as in the last proof as before. Jm plus 1 is contained in radical L prime. No? This is the same trick as before. This monotonous property of deriving. So J m plus 2 is contained in the radical of L2, and so on. So by definition, the radical itself is solvable. So maybe there is an n such that the nth derived subalgebra of the radical is 0. And then if we take these together, j to the m plus n is contained in 0. So this is 0. So we found some exponent, some natural number such that jm plus n is 0, and in particular, we've shown that j is solvable. Well, this is just a definition of solvability. Well, and now by definition of the radical, j is contained in the radical of L. Well, why? Because radical is the greatest solvable ideal. Again, I don't prove everything. One would have to prove that J is an ideal, but this is easy. Blah, blah. So J is contained in the radical. So J bar, this occurs by quotienting out the radical. So this is 0. So this is what we had to show. Any solvable ideal J bar is 0 in this quotient, so the quotient is semi-simple. Yeah, that's it for today. Any questions? Go ahead.
Yeah, on the existence of the radical, and that there is a maximum element, which we...
Yeah.
That really depends on the finite dimensionality.
Indeed, yeah. So, yeah, when I talked about it, I started thinking about it also before I hadn't.
Yeah,
so
quite that will really depend on.
Yeah. So at least
what a maximum dimension.
Exact. Yeah. So otherwise, yeah, I don't know whether it's true or not.
Is it true?
Yeah, well, one would probably try to employ Zorn's lemma, but still, it's not clear. No, by Zorn's lemma. Yeah, Zorn's lemma always only shows that there is a maximal element, but we want the greatest element, so this is stronger. So, well, no, in this case,
maximal, but still not the whole.
Yeah.
Algebra would do it.
Maximal would, in fact, okay, so it's true, yeah? Exactly. So by Zorn's
as long as
lemma,
it's not the whole. We need to argue that it wouldn't be the whole algebra.
no, if it was, no problem. So, so remark, maybe I just, I forgot the number of this thing. anyway, for existence of rat L we do not need that the L is finite dimensional. Namely, say, let S be the set of all solvable ideals. So I want to apply Zorn's lemma. So say let S tilde a subfamily of S totally ordered. Okay. So this is the crucial thing here, whether we can apply Zorn's lemma actually. So I need a totally ordered subfamily.
The iterated sums.
But, excuse me?
The iterated sums.
The union of we want to use here the union of all, and then it's it's not. Well, let's just I just write it down, but maybe it's not true, huh? So how I would usually apply Zorn's lemma is as follows: fix any totally ordered subset, and we have to show that the following thing is the ideal of all ideals J contained in this totally ordered subset. This is solvable. Right? So if we can prove this, then by Zorn's lemma, this set S would have a maximal element, but this in fact has to be the greatest element also because of the proof I showed in the, so let's draw the lattice here. S, so this is the big elements on top, the small elements on the bottom. So here is some maximal element. There are, so the dots correspond to ideals. We have some maximal ideal here, maximal solvable. So suppose there is somewhere another solvable ideal